planning. In this particular sessions, I will talk about the concept of geographic information system. We will see what is the basic definitions and what are the components of GIS and how this particular technology can be used for the urban planning activities. Some of the basic case studies also I will be showing you how the management information system of any city can be integrated with GIS database, and further how we can analyze this data and can derive the meaningful information for its geographical distribution in a city. So if you see GIS, which is also known as a geographical information system, or sometimes we also called it a geographical information science or geographical information studies. There are various names we will be using for GIS. In general, this is basically an information system which is about the place on Earth's surface. So we talk about the geography and the location of a particular point or area of interest. It also gives us knowledge about what is, where and when. These are the three questions it can answer: what is available, where it is available, and when it was available, or when it will be available. So basically, it is giving you the query like locations, which will be answered through the where, and when will be related to your time. So here, when you are using the S of GIS, like geographic information, if you study it as a system, then we will talk about the technology. Here you can see here, if it is a geographical information system, then it is a technology. If we are talking about the science, geographical information science, then it is a concept and theory we are learning. And when we are saying that studies, then we are talking about the societal context of this particular topic. So these three S are very important when you are saying I am learning GIS. So in which reference you are talking, that plays a important one. So now I was talking about three questions, what it can answer. So these questions further let us try to understand. When it is a location, so query is what is available at this particular location. And second is a condition, you can see here, and this condition is where is it. So we can find these questions, and the next question will be what has changed since, that is basically trends. So for example, what is changing, or in case of urban studies, if you take it, how the city is growing since last 30 years, in which direction our city is growing. Or if you want to understand this kind of temporal changes in a particular location, so you can use this particular technology. And the next question what it can answer is basically talk about the pattern. Pattern is basically what special pattern exists. So one I was talking about the trend, second is a patterns. So what kind of pattern it is giving us? So is there any rules, or is there any relationship are existing, or can we derive some relationship between the different growth objects that we can study in this particular subject. Another important point which is being studied in the GIS is modeling activity. So modeling, basically idea is, if you see the definition of model, it is a abstract representation of the reality. Whatever we are seeing in our geography or in our earth, can we model it in our computer system? Or when we are creating the model of this particular geography, so can we understand or can we predict something for the future? For example, a typical map in GIS is a model of your real earth objects, or is a model for your reality. When we are converting our geography into map, then we can say the map itself is a model. So in this case, if I am creating a map of an existing system, by applying some trends and patterns and condition on this particular map, can I predict or can I create a map for futures? So that, for example, if I have the land use map of last 30 years, or by making some relationship or by understanding the trends and pattern in this map, can I predict the future trend or future land use map of a particular geography. So this kind of modeling exercise we can do in our geographic information system. If you understand this particular technology GIS, today we are also using the term called geospatial technology. Geospatial technology, and sometimes it is referring to GIS only. It is basically have the three major components you can understand here. One is a GPS or GNSS. GPS is a one typical example of GNSS. In general, GNSS is a basically global navigation satellite system. So here various options available. GPS is one of the example for this, which is basically maintained or developed by United States of America. But similarly, we have other navigation systems like GLONASS you have, Beidou from China, or recently in India we have started Indian Regional Navigation Satellite System, that is IRNSS. Already we are in a progressing stage of this particular activity. In another 1 year time period, ISRO will be operationalize this particular regional navigation system in India. So that is very important point here. It is one of the most important input for our location information in the geographic information system. If you see the definition wise, it is a system of Earth orbiting satellite which can provide the precise location on the Earth surface in the form of latitude and longitude. So here the accuracy also matters. So sometimes it is 100 meter to sub-meter or sub-centimeter accuracy you can achieve through this GNSS technology, either through GPS or IRNSS. The next important component in geographic information technology is remote sensing. The remote sensing is one of the most important input for your GIS. Basically, most of the time we'll be using the satellite or aircraft to capture the information about the Earth surface, and digital ortho images, a key product that is basically map or a digital photo, what we can see here. So remote sensing is giving an important input for geographic information technology in the form of the satellite imagery or sometime in the form of the map also. Now next component of this particular technology is GIS. So GIS basically it is a integration of software system with capability for input, storage, manipulation, analysis, output display of the geographic data in the form of map or information system. So if you combine these three technology together, then we can say it is a geographic information technology. And GPS and remote sensing are source of input data for GIS. And if you see in these three components, first and second part is a input for third components. Now let us have a very intelligent definition of GIS. If you search in the literatures or go to the library or search in the internet, you will be getting thousands of definition of this particular technology. But the most appropriate technology, you can say that it is a system of integrated computer-based tools for end-to-end processing. And when we are saying the processing, it includes the capturing of data and storage of the data and also retrieval this data as information. As you may be knowing that the processed data is known as information. So GIS will give you a processed data as information which you can retrieve through many tools available in the GIS, and also it will give you the capability to analyze this data and also display or present the data in a meaningful way in the form of the map or information system or any other reporting system, charts and all. So it uses data of the location specific data, basically data using location on the Earth surface for interrelation in support of the operational management, decision making and scientific activities. So these are the three major activities which will be supported by GIS, is basically operational management, decision making and scientific studies. And it is a set of integrated tools for the spatial analysis. So there will be some existing tool available, and also you can modify this tool as per your requirement. It also includes end-to-end processing of the data. So how to process this data? So what algorithms are required to process data? That is also part of the GIS. It has the storage, capturing, storage, retrieval, analysis, modification and display of data. This is also part of the GIS activity. It uses the explicit location surface to relate the data. It aimed at decision support as well as ongoing operations and scientific inquiries. So when you are saying the decision support, the GIS is not a complete decision support system, but it provides the tools for decision support system, which is basically designed to support the management to prioritize the available alternative in your study area. So if you compare this particular technology with some of the existing related systems like your database management system, automated mappings, AM, facility management, CAD/CAM or scientific visualization, there will be slight difference between the GIS and this technology. Let us take one by one. If you take the database management system, so a typical management information works on the database. It contains the implicit but not explicit location information like city, country, zip code, etc. But no geographical coordinates will be existing there. In database management system, you can store the data, you can store the address of a particular location, but the coordinate will not be available there in the tabular formats. So it is a typical examples where the location information can be stored, but the coordinates will be missing. So then you can see that there are few more examples exist there. You can also find out that in the 2 kilometer north directions, you can also find out what is that in the 5 kilometer of south directions. These kind of queries are possible, but only we can store this information as a attribute. So it makes a difference between a tabular data or database management system and GIS. GIS will also have the DBMS as one of the integral part of the geographic information system. Now if you see the automated mapping, so primarily two-dimensional display device like thematic mappings. You can see there are different techniques are available to generate the map, and here the idea is only to generate the map only for printing the atlas. So AM is basically automated mapping techniques using which you can simply generate the map in the graphical format. So but AM can also be integrated with GIS. GIS also can give you this AM facility for automated mapping techniques, but is not only the mapping or map creation technology as per se. Now if you see the facility management system, it's lack of spatial analysis tool. In facility management system, the spatial analysis will not be available. The next technology what generally we are using is basically CAD and CAM, basically computer aided design and drafting. It basically work on the 3D graphic creations, or we can say sometimes the engineering design. You can create the map in the CAD also. You can create the map, but if you compare the simple map creation in CAD and map creation in GIS, you will be finding that GIS is having much more utilities, much more tools, the database is existing in GIS, but database is not part of the CAD. So this is basic difference. And the scientific visualization system is also similar technology, like it has the sophisticated multi-dimensional graphics, and you have lack of database in this system, lack of two-dimensional spatial analysis tools. These will be not available in the scientific visualization system, but it is existing in GIS. Now if you see here, the database, AM, FM, CAD, CAM and scientific visualization, if you combine all together, these things you can get into GIS. In geographic information system, right from the data creation, data management, the map making technique, the facility management, or CAD or like computer aided design or drafting for 3D and 2D maps, and the scientific visualization, all are the integral part of your GIS. Now the next question arises, why we should use GIS? Why this particular technology is required? Now if you see here, today we live in two environments. One environment is a natural environment and second is a man-made environment. In natural environment, you can see here so many natural features are shown here, and if you see this natural environment, it is a self-regulated environment. And the other side, we have the man-made environment which is regulated by the human beings. We are designing, we are maintaining, and also we want operate it the way we want. So here you can see here these two environments are increasingly conflicting. So there are some conflicting requirement in these two environments and how to make the balance of it. And next you see here in the geography or in the environments, we are using a different languages to describe our environments. For example, sometimes we use the cartography to represent our environment or to represent our geography. And the cartography can give you the beautiful maps or the printable map in the form of the atlas. Then sometimes we also use sometimes the mathematics to define our geography. So mathematics is another language sometimes being used to define the environment in the form of some mathematical relationship. Sometimes we use the music to define the geography or environments. We use the art. We represent our environment through the diagrams. Sometimes through some literatures also it can be explained. It can be described through the literatures. It can be described through the models. You can represent the environment as a model. And the photography, you can take the photographs and you can show that my landscape looks like this or my park looks like this. So it can be used, photography can be used to describe your environments. You have the taxonomy and sometimes the software technology, we have the statics, and there are so many languages are available today to define or to describe our environment. And also you can see that, and also we can organize our reality by using this particular technology. And in our environment, it's changing rapidly, we know it. It is becoming increasing challenge. If you see the population and the climate change, the temperature variations, loss of forest, there are many such challenges are available. And today, and these challenges are basically increasing due to the increasing of population and the resource consumptions, development and globalizations, political and social controversies. We have some technological changes, and these are basically threatening to our climate, our biodiversity, our natural places, and our stability and security, and of course our health also. So these affecting the possibility of our futures, sustainability of our environment. So due to these reasons, we are evolving towards a more human controlled environments. So this is basically our objective today. You see the entire development in this earth we are trying to control our environments, and when we are trying to control our environments, so there are some issues like populations, energy exhaustions, industrialization, pollutions, and due to this the dying things are our resources, our natural areas, diversity and civilization, and these things are creating a problem in both in the human and also in our environments. So by keeping these challenges in mind, so what we require to meet this challenge, we need to have a common vision, building a digital abstraction of the earth. So what we are trying to do here, we are trying to build a digital abstraction of the earth to understand the earth as a system. To understand the earth as a system, we need a better way to represent it, to understand, manage, communicate our world as a system. And if you see here, an evolving system here in the GIS or a geography information system is basically, it provides you the tools or opportunity for the measurements, monitoring, modeling, planning, decision making, management, and it can affect our planet's evolutions. And geoinformatics or GIS provide the framework for this. If you want these activities, right from the measurement to the management, the geographic information system or geoinformatics can provide you the framework for this purpose. Now if you see what we are doing in GIS actually, in geographic information system or geoinformatics, it is basically is known as a advancing science. So here in this particular slide, what I am trying to show you, it starts from the observation of the earth, either through the satellite technology or any aerial technology. So once you observe or through the satellite image or some other methods, so then you need to measure it. So when you are measuring it, then you have to apply some mathematics on this, and once measurements can be defined and can be fixed here, so then analysis are possible, and the analysis will be considered as a next step in GIS. Based on this analysis, whatever output we are presenting, and these output can be used for planning activity, and once we plan it, then this can be used for taking the action. And basically here trying to solve the problem related to geography, and these are the important component: observation, measurements, analysis, planning, actions. And we are applying science and information technology for many applications. Here it is basically integration of geography and information technology. If you break this particular word geoinformatics in three parts, it's geo related to geography, infor means it's information technology, matics is basically mathematics. If you combine these three technology together, it will be known as a geoinformatics. Some of the example application of this particular technology, you can see, for example, the urban planning and management and policy. This particular topic will be covering in detail during this particular due course of time. And then we have some of the environmental studies. You can see here number of topics are listed. We have the civil engineering utilities. Some of the areas are identified here. In the business, how we can use GIS. Education and administration, how we can use the GIS. Real estate, healthcare, another interesting area like health GIS. So there are many such applications exist where the geographic information system or geoinformatics can be used. Now let us have a brief idea about this particular technology, and we'll have the overview of it. If you see here the knowledge base for GIS, it has the three components. One component is basically a computer science or basically management information system. This particular technology is represented by this ellipse here, like electrical shape. This I have shown here circle. Basically it is a graphics. It can provide the visualization, database, system administration, and security of this data. And if you study these three, four or five component, it comes under computer science category. The geography will provide you basically the cartography tools, geodesy, photogrammetry, landform, and spatial statistics. And the application area can be many, like public administration, planning, geology, mineral exploration, forestry, site selections, marketing, civil engineering, criminal justice, and surveying. These three circles and the intersected area of these three circles is known as a GIS. Is the most common things in these three technology will be known as a GIS. Now, if you see the further component of this particular technology, here these are the different boxes are shown here. The most important component of GIS is database management system. The database is a core strength of GIS. Without data, the GIS is not having any existence. If data part you remove from GIS, it looks like a simple CAD or simple drawing format of your map. So here the data can be your external or internal data, and it also includes the attribute and the spatial data. When I am saying the spatial, it is basically your locational data. And once you have this database management system in place, so you will have a database management system for the spatial and non-spatial data. And then the important component of GIS is a model management system. Basically various modeling techniques are available and different data models are available to present your data sets. We'll be discussing about these data models in coming slides. And then another important component is a knowledge management system. It is not an essential component. It is basically an optional component of GIS. Once these all things are integrated together, then what you can do, you can set up a dialog management system. You can have a analysis system like based on the attribute based query. You can have the location based query, and also you can generate the reports in the form of the tables. You can generate the reports in the form of the graph. You can also generate the report in the form of the maps. On the basis of these reports and output, you can have the information system, and also you can have the decision support system for the decision maker and planners. So these are the all about the GIS components, and here if you derive the major technical component here, you will be knowing that the most important is database, which is known as a database server for the data management activity. Then we have the application server for data processing, which we are doing through the software technology for data processing, analysis, and data presentation. And of course, the third important component will be your hardware. Now here, GIS system architecture and component. If you try to understand through this particular slide, you will see here the most important is our data inputs. And the data input, maybe you can use here the remote sensing technology, or you can also use sometimes the in situ observations from your grounds, and this data can be you can input into your system. And once it is inputted here, then you can set up a geographic database. And based on this geographic database, you can take the input for the query. So query, basically you are asking to the system, so please give me the location of this particular object. Or you can ask the question, for example, I want to know all the schools within 2 kilometers of my range. So this is the input, it's called as a query input, and first input was known as a data input. And once it is done, so here the output of this query can be in the two forms, like display and reporting. You can display the output in the form of the tables. You can also display the output in the form of the maps. And then transformation and analysis will be another important part of this entire activity. And transformation, basically the transformation of data from one form to another forms, and second is to analyze this data and derive the meaningful information out of this data. If you try to understand further, to do this exercise in GIS, we have the different data models. And this data model, as I explained in the beginning itself, model basically we studied about the abstract representation of the reality, and the basic purpose of this model is basically allows the geography feature in a real world location to be digitally represented and stored in the database, so that they can be abstractly presented in the form of the map form, and can also be worked with and manipulated to address some of the problem related to geography. So basically the purpose of the data model is how we can fit or how we can bring the geographical feature in our computer system. So how we can present our geography in the computer system, that will be the major objective of the data models. If you see here the typical examples, how it looks like in a reality, real world locations. In geographic features, you can understand here different features are shown in this particular image, and abstract representation of this feature when you are showing is basically in the form of the map. This is a typical model of your GIS. Now come to this particular example here. Few more examples are shown. So how it can be integrated. You can see here that this is a typical simulated image of a geographical regions. Here different landforms or different feature in geography are shown, like you can see this model, some trees, the ground, and you are able to see some buildings. You are able to see some of the road network here, and some other geographical features like mountains. You have some grasslands, and these all locations are basically simulated in your GIS, and it is one of the output of geographic information system. It is not necessary every time, so GIS will be giving the output as a map. Sometimes people confuse that, is GIS a map making technique? GIS can produce map for you, but GIS is not a only map making technique. Map is only one of the output of GIS. So how we are doing this? Basically we are using the concept of the layer. This you can see here. This is the concept of the layer. If you stack all the layer together, then you can present your geography in better way. And I will come back to this layer concept in later stage. Let us try to see few more examples here. This is another examples which I am displaying here. This particular example is showing you the three-dimensional view of a geographical terrain. And this here, although we are not able to see all the buildings or trees or playgrounds properly, but it is giving us a synoptic view of a particular geographical regions where the different features like your mountains, your rivers, your barren lands, you have some forested land. These areas are clearly shown, and this is also one of the output of the GIS, and these outputs can be used for different purposes. For example, this is a very high quality output, but here the quality is not that much detail, but at least top level planning, it can give me a lot of information about my study. The another method also you can see here, the another abstract representation of this geography is shown in another example, where the features are shown in a basically in drawing formats, not exactly the 3D view, but in the form of the drawing also we can show our features in our output of GIS. Now let us come to the concept of the layer. So basically the GIS data model implementation, how we are doing here, you can see here, suppose this is a globe, a complete geographic regions where it is draped with the satellite imagery. Now if you are willing or you are interested to define or to show the administrative boundaries, for example in India, right from national or country level boundary to the state level to district level, then taluka level, then further in the village level. And these boundaries are defined at the different administrative levels. So when I am talking about the administrative boundary, so this will be considered as one of the layer. Basically layer is a theme. I am defining a theme. When I am defining a theme, it also includes the geometry. So by using which geometry I am going to define it. For example, if it is an administrative boundary, I am saying that, so in data model we will be using the polygons. Basically it is a closed area which will be representing a administrative unit. So here the boundaries will be always shown as basically polygon features, but another important is utilities. Very important points. I want to show what are the different utilities available in a particular administrative boundary, and now these utilities can be represented as a point features, and also can be represented as a line feature, and also can be represented as a polygon features. Now I can overlay on top of the administrative boundary the utilities. What are the utilities available in this particular geography? Then next level I can go in the case of the urban planning, in the ward level, and I want to display all the wards on top of this administrative boundaries. And ward boundary also can be considered as one of the administrative boundaries. But it is not necessary every time I will be representing my ward as a polygon only. So sometime this ward can be represented as a point also. The ward location, a center point can be identified just to represent the location. And up to this ward, I can also define the buildings. And again, most of the time we will be defining the building with the point. But actually buildings are not point. It can be also defined as a polygons or sometime as a box. As a 3D view of the building also can be defined. Then further, if you are trying to study in the slum level, then further you can also define the slum as a layer. The slum is a one theme what we are defining here. Then hydrography, then street, digital orthophoto, all these category if you are theme wise we are categorizing, and these are known as a layers actually in GIS. And if you combine all these layers all together, then you will have your own geographic information system. And then by combining these all layers together, you can derive some meaningful information, knowledge, or you can also do some planning activity. So I hope the layer concept will be clear here. And data is organized by the layers, coverage or themes. These are the three terminology we are using here. Sometimes we are saying it is GIS layer, sometimes we are saying there is a GIS coverage, sometimes we are also saying it is a GIS theme. These are the terms basically we will be using in GIS. And with earth layer representing a common features. Basically a layer means it is a integration of the common features in a particular GIS data models, I can say. So layers are integrated using explicit location on the earth surface. Thus geographic location is the organizing principle behind this layering concept. So basically we are using the geographic location as one of the important component for creation of the layers. Now let us try to understand in details the GIS model. Some of the example you can see here. Suppose this particular piece of land, here I am just representing as a longitude and latitude. Within this latitude and longitude, I have the road features, and the road feature in general is represented by line. And by when I am representing this road as a line, and also sometime I can represent hydrology as a line. I can also hydrology, for example, your water, river, drainage as a line, and topography like your contour lines. These also can be represented as a line. So this is one typical example of representing the line features or line layers in your GIS. Then you have the hydrology. For example, if you are representing hydrology, you can see here. So continuous the drainage lines or maybe river boundaries. These are also being also used for this. And then topography, I was giving example for this is this one, like a contour lines, and they can be related because precise geographic coordinates are recorded for the earth themes. Layers are comprised of two data types: is a spatial data which describe the location, means where it is available, and second is a attribute data which specify the characteristics of this particular feature. Very important point. Here two components we are studying. One is a spatial, second is a attribute. The spatial data is giving you the information about the location where it is available, and the attribute is giving you the characteristics of this particular feature. So here two models will be talking about it. One is a vector data model, second is a raster data model. So we'll see in detail what are these two data models. And here some of the important parameter what we have to keep in mind is basically projection, scale, accuracy and resolutions that we'll be talking about in coming slide. Now you see here I was talking about the two important component of the data model. One is a spatial, second is attribute. So sometimes we are saying that it is a spatial and non-spatial. So non-spatial basically we talk about the attribute data which gives you the characteristics of particular feature. The spatial data, it gives a specifies the location stored in a safe file or sometimes geodatabase or similar geographic files. Basically, safe file is one data format which is commonly or most of the time the GIS professional will be using to store their location information. So safe file is basically a open proprietary, it is an open format, not proprietary right now. So initially it was developed by ESRI, and now this is being used by most of the GIS professional to define or to store your location information. Another interesting model which is known as a geodatabase or GeoRDBMS, which is also being used in GIS, is basically to store our geographic features or in a database management system. And here the idea is basically to how to handle or how to address the multi-user environment, and which is known as a geodatabase or GeoRDBMS. And in the attribute features, basically you describe data, what, how much, when it was available, and basically it talks about the characteristics of that particular location of or feature. And then we'll be storing this data in the form of the table basically. So attribute data is being stored in the tables, and the spatial data is stored in the form of the safe file, you can see. So GIS system traditionally maintain the spatial and attribute data separately. Then they join them together to display and for the analysis purpose. So basic idea is here you will create the spatial data different and attribute data different. For example, if you are creating the map by using the satellite imagery, so first you will do the defining the coordinate system or projection and all. After that you will be identifying the features and you will be creating the shape, basically location information, and you will be storing in the spatial domain. Then the attribute basically you will be deriving by based on your ground truth survey. So attribute most of the times are being collected using the ground survey. So attribute in general will not be extracted using the satellite remote sensing or remote sensing technology. It can give you the feature is available as a building, but this building belongs to a school, or this building belongs to a shopping center, or belongs to a hospital. This information will come from the ground only. Either it is a hospital or a school, this information you cannot derive from the satellite image. So attributes play a very important role, and when you are collecting the attribute through the ground survey, and feature through the satellite based remote sensing or satellite based survey, then how to integrate these two data or two type of data set together to derive the meaningful information. That is one of the most important or interesting tasks what we are performing in GIS. Now I was talking about the two data model. One I talk about the raster, second is a vector data model. And in the raster data, if you see here, it is basically a GIS format. It represents information in the form of the matrix. Basically in the pixels you will be storing the information. And the areas are basically a grid of the equal size, which is known as the pixels. Equal size square cells you will be using to represent your geography, and the attributes are recorded by assigning each cell a single value based on the majority features, and that will be known as attribute. All the cells defined in this particular image will have some information, or digitally we will define these attributes for each and every cell, and these attributes or this digital number or digital value will be used to analyze the characteristics of this particular cell in a raster data model. Image data is basically a special case of the raster data in which the attribute is a reflectance value from the geomagnetic spectrums. Cell in image data often called as a pixels. So the typical example of your photograph, for example, you are taking from your mobiles nowadays. If you see this can be considered as a completely raster image. The similar kind of image capturing through the satellite remote sensing technology also. But the another data model which is being used in GIS called vector data model. It is the fundamental concept of vector GIS is that all geography features in the real world can be represented either as a point, line or polygon. Here three geometries are being used to represent your geographical features, and the vector data model says that these geometries are more than sufficient to define all the features in this geography. For example, the points or dots, you can define the trees, poles, fire plugs, airports, cities location in the coarser resolution image or maybe higher scale maps, and the lines like stream, streets. You can also see civil lines. This thing you can define using the line features. The area polygons are like land parcels, cities, countries, forests, rock type. So because representation depend on the shape and the size, like softwares like ArcView and ArcMap and these things will be using to create the shape file of this vector and vector data models. Now, concept of vector and raster you can understand better way here. Suppose this is a real world. Here you can see in the real world, this is basically a river, suppose, and here some trees are shown and some of the house locations you can see here. These are the some tree, and I want to model this geography in my raster and vector model. So here these are the outcomes. You can see here in the raster representations. In this, for example, this is a house. This house is represented as H in this particular pixel. It belongs to this pixel sometime, but not necessary that one house will come only in one pixels, or it may have the group of pixels also. So here in case of tree, you see here the trees are shown in this pixel or group of pixel, and then the river is this way in the pixel format it is represented. This is for raster. Similarly, in the polygon, the data model will be this way, like polygon is this is the polygons, this is a closed points, and point is here representation of house, and similarly for group of trees are represented as polygons, and then the entire river is represented as a line feature. So you can understand better here. So how the real world geography it can be represented in two data models in different way. So I also mentioned about these four important characteristics of your geographical data models. Basically, we talk about the projection system, we talk about the scale, accuracy and resolution, and the projection is one of the important activity what we will be performing in GIS. Is basically a method by which the curved three-dimensional surface of the earth can be represented in a two-dimensional coordinates x, y on the 2D flat map or screen and basic idea here is the 3D model of a world, how it can be represented in the form of the two-dimensional output like map or in the simple screen. And here the basic objective is to, without losing the accuracy for the measurement, we have to apply some mathematics on this, and this is known as a projection system. And the next important point is a scale, the ratio of distance on the map and the equivalent distance on the ground. So basically it is a ratio between two distance, one is in your map, second is the reality. In theory, GIS is a scale independent, but in practice there is an implicit range of scale of data output in any project. If you see, the GIS is a digital format. Here there is no concept of scale, but when you are recording the data, when you are creating the data, you have to define the scale. So basically scale is related to your resolution. Yesterday I think it was covered in the class that what is the relationship between the scale and resolution. So when you are talking about the satellite imagery or image data, that time we will be using the resolution to assess the accuracy of this particular image. But when you are converting this image into the form of the map, then you will be using the term called scale to assess the accuracy of your map. So here the difference between the map and satellite image will be resolution and scale. These two important difference you have to understand every time. Whenever you are saying that I am talking about the accuracy of map, then you will be talking about the scale. When you are talking about the accuracy of the map, you will be talking about the resolution. But again there the resolution will be many. There are four types of resolution like spatial resolution, spectral resolution, temporal resolution, radiometric resolution. These all resolution will define what kind of or what quality data you are getting from the satellite. And next important point is accuracy. How well does the database information match with the real world? Very, very important points. GIS will not give you the simple drawing. When you are creating the map in the GIS, the accuracy also plays a very important role. Here, different type of accuracy we talk about it. It's like a positional accuracy. We talk about the consistency in the database. We also talk about the completeness in database. These accuracies are playing a very important role when you are creating the data in GIS domain. Resolution already I talk about it. So here you have to remember that the projection, scale, accuracy and resolutions are very, very important when you are creating data in the GIS domain. Now these are some of the examples for your data formats. Like for example, if you are taking the raster example, you can take their TIFF or GeoTIFF data format. You can use the JPEG 2000. You can use the GML. You can also use the web service format like WCS and WMS. I will be talking about these data models in detail in one of my lecture during this course. And for the vector data, we have a format like SafeFile. We have format like PostGIS. We have format like GML, KML and WFS and WMS. Again, these two formats belong to the web service category, will be covered in some other class in detail. So these data format always you can remember here. So let us take example of layers and data models, accuracy, projection system and all in one by one. Now you see here, I am showing you one small piece of land, maybe some of the slum area or maybe some urban features. Here all the features you can see very nicely, like your buildings, you can see the your trees, you can see the open area, ground, you can also see some of the lanes in this area. And in the satellite image I can differentiate it. But when I am extracting this information in the form of my GIS layer, you can see, for example, if I am extracting a line and polygon feature together in this particular image, you can see here, all the line and polygon feature can be represented sometime as a polygon or sometime as a line or point features. And same time, if you are extracting only building, as I was talking about it, that building can be represented as a point. But when you are working in a high resolution satellite image, where you can also calculate the area of this building, or you can extract the footprint of this building, the building always can be represented as a polygons. So this is a typical example of the representing the building as a polygons. And here you can see this particular image is a raster. These outputs are basically vectors, And when we are creating the digital ortho image, this is one technology what we will be using in GIS called ortho rectification, is basically we will be correcting this image with respect to the height. Because when I am considering this particular image as a flat image and I am not considering the height information, or I am not calculating the height when I am calculating the length of a road, then the accuracy of my GIS data will be very less. To improve the accuracy of my mapping, so I will be using the ortho rectification technique. Basically, I will be using digital elevation model to correct my satellite image with respect to height by applying some of the some mapping principle like spatial referencing system like UTM and WGS84 is a datum, projection datum system, and the resolution you can see here like 0.5 meters, accuracy 1 meter I am getting, scale is 1:500 scale. So this way these parameters will play a very important role to derive the accurate data from my satellite image. So once it is done, so I can overlay based on the common geographic locations. If these projection system datums and SRS are not defined, so it will not overlay in this way on top of the satellite image. You can see here the exact boundaries are now identified. So overlays are possible, and once it is done overlay, so you can see here, so what you can do here, you can identify the points, you can also see the different nodes, and you can also then fire some of the analysis queries. If, for example, this yellow line what I am showing here, it can be considered as a buffer range of this red center point. So you can say that within few meters of this particular point, what are the features available? So output is this attribute. So this is known as a location based query or location based analysis. Then you can also generate the 3D view of your geography. Here in GIS, Geo-visualization and Query on the web, you can see here the complete 3D view of the city is presented here. You can see all the houses in the 3D view, the tree structures, you can also see the road and other landform here in the 3D GIS. So these are the basically one typical example of the anatomy of GIS database. So this way, by grouping the different features in database, we are organizing it. This is a typical structure of data organization in GIS domain. And it's not only the attribute data, it is also the raster as well as vector data. So basically three types of data we are organizing and managing GIS. One is basically your features, which is known as a vector, and second is basically your attribute, which define the characteristics of your feature, and third is the raster representation of your terrain, which is basically in typical GIS is a satellite imagery in the form of the high resolution or coarser resolution or medium resolution, whatever it is, so that can be stored and can be part of your GIS database. Now let us try to understand how this particular technology will be useful for the urban planning activity. So here I can say that it can be applied to many type of problems. Among these are the representative of the both raster and vector data based structures, both simple and complex analytical models. Master planning applications are one of them. So when we are preparing a master plan for a city, so this can be considered as one of the typical exercise which can be easily done or it can be easily carried out using the GIS technology, especially for the area monitoring, both on this the sectoral and integral basis. Regional potential and feasibility analysis and the site selection studies can be performed using this technology. For studies in which the plan alternatives are generated, much more flexible design, optimization and evaluation tools would be needed in order to give GIS a dominant position in the development process. So you can generate the different planning scenarios, and based on your characteristics, based on your priorities, alternative, you can choose the best plan out of it. So different kind of scenario you can generate for the planning activity, and then it can also be helpful for the documentation of the spatial plan and in the approval process of the developments, building and installation permits. So you can also use this particular technology for giving the permission for building creation, and also the preparation of any like infrastructure development activity like road networks, sewerage, and also some of the alignment of the your pipeline, and all this activity can be performed here. GIS applied to a wide range of land management and land use planning issues, including the interpretations and formulation of land use policies. Land use policy can be interpreted within GIS using modeling approach. Here the modeling exercise, it can generate the different scenario for it. Some of the output in the form of the maps showing in the area which land use changes are more likely to occur, and the statistics can show the graphical representation, tabular summarizations, this information according to a variety of special units. Such output allowed land use implications to be discussed. The predicted land use change can also be input for GIS based impact assessment. So you can also generate the possible land use scenario for the future also. So here when you are applying GIS for urban plannings, so what are the important considerations we should keep in mind? Basically, designing a GIS framework is mandatory. When you have any plan how to use GIS for urban planning, a framework designing is very, very important. Here in this particular circle, I am trying to you what do you mean by framework here. You can see here the framework is very important, right from national to slum level studies. If you are doing, what you can consider here for the national level planning, if you are creating the maps or you are creating a GIS, so generally we are talking about the scale of 1:250,000 scale. So in this case, your projection system, generally in India we are taking Lambert conformal conic and datum as a WGS84. And when you are going for the state level planning, for example 1:50,000 scale mapping, then in this case the projection system for some of the state in India we are taking the Lambert conformal conic, or some of the state it is taken as a TM, but datum as a WGS84. Then go for the city level, then you can see here the projection sum is completely changed from the LCC to UTM. Because if you learn the projection system, you will see that the different type of projection systems are used for the different purpose. Some projections are basically focused on the preservation of your area. Sometimes preserve the size, sometimes preserve the directions, shape. Based on this, projection systems are being used. For example, here the city planning, which talks about the 1:10,000 scale kind of mapping. Then projection system we are using the UTM. Here the UTM zones are defined for a complete world. So based on this you can decide. Then further, if you go to the slum level mapping 1:100 scale, then again the UTM and WGS84 datum is being used. This is one typical example about the framework. So here the important consideration is basically when you are designing your GIS for the urban planning activity, the most crucial point is how you are defining the framework of your data sets, so that your data can have the interoperability between the different scales, different resolution, and different data types. That is very important consideration. So that already I discussed about it, 2D and 3D GIS, and this is one of the use case. Maybe our other experts will be using this particular case for more explanations. So I am just quickly I will go through it. Like if you are taking the high resolution satellite data, so first you have to do the georeferencing, then you will be doing the GIS mapping like land cover, so slum mappings, boundary identifications, transportations, vacant land, vegetation, and all you will do it. After that you will be doing detailed slum and infrastructure mapping using the total station survey. It is not necessary every time that remote sensing technology will be giving you the highest accuracy output. Sometimes the total station survey kind of technology can be used for this purpose. Then you will be integrating your existing attribute data, what generally you are practicing in your urban planning activity, and you will be linking with your spatial data. So then the DPR preparation and this all activity can be performed. This is one typical example where successfully we have implemented GIS in India in many of the projects. So like for the slum area study for high resolution satellite imagery, you can see the identification of slums in the urban planning area, then overlay the this footprint of these buildings, and then perform this some attribute based query. And you can see here the cyan colors. I am firing the query in this table, and the outputs are presented in the form of the different identification of different feature. You can see here that is shown as a cyan color, and normal features are shown as a yellow color in this map. more queries when you are integrating your MIS and GIS together. So directly, basically, both way query can be fired, like location based query and the attribute based query. So many more such queries and GIS analysis can be performed, so output can be presented. So that's all about this particular topic. So I have not gone through in the technical details, basically how we are creating the data and all things, but I have given you an idea that how this particular technology is being used, what are the different standards for that, and then further in the urban planning, how people are using this technology and what kind of output you can derive from this. So thank you very much.